Okay, so we're going to go over these questions as best we can in this video. And so I'm going to read through each one of these questions and explain them just a little bit. Some of them I'll go through in a little more detail, especially if they require some math or have some connection to broader topics or understandings or things like that. Okay, so first with 116. The main issue about this question is that the coefficient of kinetic friction doesn't change. It is a constant. It's found in your reference table, which means it must remain the same as we look at these examples, right? So for any given situation, whether it's steel on steel, it doesn't matter the size of the steel, the weight of the steel, the surface area of the steel. It just remains the same. All right. All right, so similar questions. These next couple questions are all kind of like dancing around the same kind of idea. And this question, if the crate was filled, right, just like in the previous one, um, it's saying the magnitude of the force, right? So this time we're talking about the force of kinetic friction, right? So this time we are going to see that it will increase as we add more stuff into it. And the reason that is the case, it is because the equation for the force of friction, right, is as follows. Force of friction is equal to mu times the normal force, right? And the normal force is dependent upon the amount of force applied to the plane, right? So if you have a situation like I'll draw down here, if you have a block on a plane and you have a bigger block on a plane, right? This one will have a small force of gravity, and this one will have a much larger force of gravity. That means that this second option here is pushing on the block, or excuse me, the block is pushing on the plane more, which means the plane has to push back more, which means a larger normal force than this little baby normal force over here. Okay, so an important distinction here between those couple of examples. And so there's that one. All right, the next one, an object initially at rest on a horizontal surface and is set into motion. So that means it starts off at rest and then it ends up in motion. So this is the difference between the coefficients of static friction and the coefficients of kinetic friction. And so the issue is that, well, the point is that when we look at our reference table, we will always see that the coefficient of static friction, so that mu, like sub s if you want, is always going to be larger than the coefficient of kinetic friction. We talked about this in class where we said that it's always harder to start something moving than it is to keep it moving, and we talked about moving desks around and things like that. So that's the case here, and we'll choose the answer that is appropriate for that. So that's one of those you kind of need to know it thing. You can look at your reference table, and if you do look at your reference table, you'll notice that the all of the coefficients of static friction are higher than the coefficients of kinetic friction. So you can figure it out that way, but here we go. So in this next example, a thrown baseball is acted on by air friction. All right, so it's still friction. I mean, the air doesn't really change anything. There's nothing like particularly special about it. Anytime we have friction, we're gonna cause some amount of thermal energy, right? So if you imagine like rubbing your hands together, you would find that the longer you rubbed your hands together, the more that they would heat up. And so why is that? It's because friction is acting on them more. And we'll understand this question a bit more once we get in and start talking about energy, but thermal energy will, of course, increase. Number 120. This question eluded a lot of people, and I think partly because you feel like I just don't have enough information. It's like I don't know what any of these blocks are made out of. And so if I don't know what they're made out of, how can I determine which two have the same force of friction? And this really just comes down to this one part of the question right here. This idea of constant velocity is super important in physics because it's always going to tell us a lot of information, right? It's going to tell us that it's a zero acceleration. It's going to tell us that net force is zero. It's going to tell us that all the forces are balanced, right? It tells us that the object is in equilibrium. That's what it means. So when an object is in equilibrium, like those things tell us that the forces are balanced, right? Those things that I just said, right? So it means that um, if this is a pushing force to the right of 2 newtons, if in order for this to be in equilibrium, the force of friction must be directed to the left at 2 newtons. Likewise, if this is a pushing force to the right of 3 newtons, we must have a force of friction to the left of 3 newtons. Right? So in each one of these cases, these experience an oppositional force that we would call the force of friction, right? And so we would initially try to say which one of these, or what is the value of these force of frictions, and we might be stuck trying to say, well, the force of friction is equal to mu times the normal force, and I don't know what mu is, so if I can find a normal force, which you could, then how am I supposed to find this force of friction? And that's the trick here. The truth is that you don't need any of these masses at all. You do not need them. They're not required to answer this question. All we need is, as we said, to know the forces have to be balanced. So if there's a force to the right of 2 newtons, there must be a force to the left of 2 newtons. So this one down here is also 2 newtons, and this one right here, choice B, must be 4 newtons, which means that the choices that have the same are choices D and A, and we're good with that. Okay, so let me just get rid of that. Oh, what is happening there? Okay, here we go. Okay. All right, on over here. A force of 10 newtons toward the right is exerted on a wooden crate, initially moving to the right on a wooden floor. The crate weighs 25 newtons. All right, so pictures here are going to be pretty important, I think, in order to make sense of this. So I'll just kind of zoom in right here. If I were you, I would not try to draw my pictures in a tiny space like this, but I'm just trying to make use of, time and all kinds of stuff like that. Okay, so this is what we have. A force of 10 newtons to the right. All right, 10 newtons. Exerted on a wooden crate. So now we know that this is a wood floor, and then this is a wood crate. And what that immediately tells us is that we can go to our reference table and we can look up the coefficient of friction here. And the coefficient of friction for wood on wood is 0.3. So that's something that I know. And it's already moving to the right, which means well, that's the other part of this, is we know we're going to use this 0.3 as opposed to the static version of this. Then finally, we're told that the weight of this crate is 25 newtons. Okay, so we have all that information. Cool. Now, calculate the magnitude of the force of friction between the crate and the floor. All right, so we look at this and we say, all right, the force of friction is equal to mu times the normal force, which means I already have mu, and I need to find that normal force. Remembering that the normal force is that force that cancels out the y direction. So right now in the y direction, we just have this force of gravity. Remember, I told you the weight in newtons, so that means that this Fg right here is equal to 25 newtons. You do not need to multiply this by 9.8 because it's already in newtons. So we have a force down of 25 newtons onto the plane, which means the normal force must be directed upwards, equaling 25 newtons as well. All right. And that concept right there is pretty easy to mess up. Just got to pay attention to whether or not you have newtons given there as the weight, or you have kilograms. If it's kilograms, you would need to multiply it by 9.8, but in this case we do not, so we have 25 newtons times 0.3 is equal to the force of friction. So I know that 25 times 0.1 would be 2.5, so then that times 3 would be 7.5 newtons. So, all right, so there's our answer to that one. Okay. What is the magnitude of the net force then? Okay, well, we said that whenever an object is moving on a surface, we know that the forces in the x direction are going to be equal to the net force, right? So what are those forces? We have a positive 10 newtons Okay, and now we have this 7.5 newtons, which is going to be acting in opposition, right? It's going to be pointing back this way. This is going to be our force of friction. It's always an oppositional force, so it needs a negative sign in front of it. So we put those two things together, and we get an answer of 2.5 newtons. All right. In this question, they're not asking you what the acceleration is, but is the crate accelerating? And the answer to that is yes. Anytime you have an unbalanced force, and this is the explanation part of it, anytime you have an unbalanced force, right, your object is accelerating. The only way to have an object not accelerate is to have an F net equals 0. We don't have an F net equals 0, so whenever the net force is greater than 0, your acceleration must be greater than 0 because F is equal to ma. And mass, that's just the object. So the only way for this term right here, your acceleration to be equal to 0, is it when F is equal to 0. All right, that's just the way that is going to go. All right, so there are those questions. All right, on to 124. Okay, diagram below represents 10 Newton block. Okay, so again, we got 10 Newtons here. All right, you guys looked a little bit about the inclined plane stuff yesterday. So I will go over this just a little bit, but I'm not going to go over inclined planes in too much detail. I'm going to make cough here in a second. I'm sorry. Okay, so again, constant speed comes up, right? Constant speed. That means whatever this force is down the ramp has to be the same as the frictional force, which will be directed directly up the ramp. So here's how we end up drawing this. First, we need to draw our force of gravity. Then we need to draw our normal force. Here's my FG. Okay, now, as we said, we rotated our coordinate system here, right? Our coordinate system is normally situated differently. Here, let's see if I can do it right here. Right, this would be our coordinate system normally. This is terrible, but and then we go like this, and we can, we would put it right here. Now in this situation, right, this is all well and good, except for the fact that we would have to find components of the normal force and components of the force of friction. So what we do instead is we rotate our coordinate system, right? And when we rotate our coordinate system, this is going to like kind of cancel out. But you notice that sort of if I had drawn it just a little bit better, or rotated it a little bit better, let's see, you'll see that the normal force and the force of friction are now in that x direction. Now, the thing that we need to do now is we need to find the components of Fg because Fg is not in x or y. So that's what our task is here. So when we draw in our components, and again when I say components, like remember when we shot stuff up at an angle, so I'd say like, hey, here's my initial velocity, it's 100 meters per second, and like here's the ground. What we would do is we would drop a vertical, and we'd make ourselves a little triangle, and we'd say, okay, well, this is my x part, my Vx, all right, and this right here would be my y part, my Vy, all right. So we're going to do the same sort of thing here. We are going to have this, let's see if I can make this even smaller maybe. We're going to have this vertical direction right here, okay? And we would have this horizontal direction right here. These two planes of motion, okay, are our new rotated coordinate system. And so what we need to do is we need to, just like we did when we had that other one, we need to like drop a vertical, right? But so we're dropping it from the tip of this one vector, right, down to this. You see how we've dropped a vertical in the same sense, right, that we did before. If you need to, you can rotate your screen to maybe see it. And so now what we have is we have a right triangle right here. All right. And this line that I've just drawn, this one right here I just scribbled on, is parallel to this line I just scribbled on. In the same way then when we dropped a vertical, that vertical was parallel to the y-axis. So we have a right triangle here, and the only thing we need to do is take this angle and put it right here, because that is how much we rotated by. All right. And now I can label these things as, well, this is now my part of gravity, because that's my hypotenuse, in my new y direction. And this is my part of gravity in my new x direction. Because I am only looking for one thing here, and because I know it's traveling at this constant speed, I only need to find this side down here. Because, as we said, whatever the force is down the ramp will be the same as the force up the ramp. So this right here is the force down the ramp. It's my FGX. And I can find that by saying it's the side opposite that angle. So I can say sine theta is equal to opposite over hypotenuse. Hypotenuse sine theta is equal to the opposite side. So my hypotenuse is FG. And then it's sine of 30. That's my angle. And that's going to be equal to my opposite side, which is my FGX. This 10 newtons right here is my FG, once again, because it is in newtons. So I just put that in right there. 10 newtons times the sine of 30, which is a half, is equal to my FGX. So my FGX is equal to 5 newtons. So it's choice 1. Choice 1 right there. That's a long, so that's a long explanation for ultimately all you have to do is what's in the green right here. Okay. So it can be a tough question, these inclined plane things, but just take your time with it, and we'll work on it, and it'll get better. Sand is often placed on an icy road because the sand, right, it's going to increase the coefficient of friction between the tires and the road. That would be the point. You wouldn't want to decrease that, right? All right. 126. When we're looking at that, force of friction is equal to mu times the normal force. A little bit more work to do, but the fact that it says it's on it's being pulled horizontally at a constant velocity again. So that is important for this question, because it is a 10 kilogram block. You can calculate the force that it's being pulled at, because whatever force it's being pulled at has to be equal to the force of friction, right? Because of that constant velocity business. So if you imagine your block and your plane, and you're saying, hey, I don't know what this force is, but I know what this force of friction is. And you say, well, how do I know what that force of friction is? Well, you were told it is, where is it? Block of ice, and it's a rubber block. So you go to your reference table and you look up the coefficient of friction for rubber on ice, and that coefficient of friction is 0.15. Okay, but now what? Well, now you know the force of friction is equal to mu times the normal force, and the force of friction is going to be equal to that 0.15. Well, what is the normal force? Remember, the normal force is what cancels out the y direction. So what is in the y direction? Well, you have Fg. So that means we just need to determine what Fg is. Remembering that Fg is equal to the mass times the acceleration due to gravity. That means it's going to be equal to 10, leading off units, I apologize, times 9.8, which means Fg is going to be equal to 98. So we put in our 98 right here. Multiply that, and we'll get about 15. Okay, depending upon what you're doing here, but about 15. So this is 14. Let's call it 14.7. I'm just trying to knock it out quick. All right. So we've got that. All right. Get rid of this stuff and move on to the next question. All right, just a few more left. All right, and these I think should go pretty quick. What is the magnitude? What is the magnitude of the horizontal force along the cart? All right, similar concept. I'm not going to go through this in as much detail, but because it's pulled, meaning this whole question, they tell you in this question. This question is always frustrating to me, and they do this a lot. But they have a picture that has nearly all the information, but this piece of information they put right here for some reason. I don't know why. Just so that you're confused by it. So that force is, that's really messy. That force right there is 10 newtons, which means the force back has to be 10 newtons. So this answer is 10 newtons. Then they say calculate the weight of the cart. So the weight of the cart is going to be Fg is equal to mg. So that is multiplying it by 9.8, so 49 newtons. Just like we've seen in a couple of this, it says what is the normal force, right? Compare the weight to the normal force. In this case, they're the same, right? Because there are no other forces in the y direction, so that's good. All right. Number 130, calculate the coefficient of kinetic friction between the cart and the floor. I guess I can do that, but it's mu is equal to the force of friction times the normal force. Well, we found the normal force right here, and because we know that this is traveling again at a constant speed, that means that we know that the force of friction also has to be 10. So this is going to be our 10 newtons, right? Because the force of friction must be backwards at 10 newtons in order for this to be moving at a constant speed, divided by that normal force of 49 newtons. So it's 10 over 49, or about 0.2. Okay, will be our answer for that. 0.2 would be equal to mu. All right. Now we're on a new set of questions here. We're 131, and our last three. A constant horizontal force of 5.2 newtons is applied to a wooden block to slide at a constant speed across a wooden floor. Calculate the weight of the block. Okay, so again, we are saying that it's that same concept. If there's a force this way and it's moving at a constant speed, meaning it's in equilibrium, the force in the other direction must be the same. So we're telling you, hey, I'm pulling it with 5.2 newtons. What's the weight of the block? Well, that means that this force back this way must be 5.2 newtons, which means that that is what the force of friction is equal to. The force of friction must be equal to 5.2 newtons. And because we tell you that this is a wooden table and it's a wooden block, it means that you know what the coefficient of friction is. You know that mu is equal to 0.3. So finishing out that question, you're saying the force of friction is equal to mu times the normal force, and you know that this is 5.2 and the mu is 0.3. And you know that it's on a horizontal surface, so the normal force, because there are no other forces in the y direction, is going to be equal to the force of gravity. So it means just find the normal force and you will have found the weight. So we finish out by dividing each one of those things, and you get 17 newtons is the answer to this question right here. All right. What are we on now? A wooden block is at rest on an incline. As the angle the incline makes with the horizontal is increased, so that means like you were like this, right? And then you make it, like this, right? Where you had angle here, and obviously this angle is like 0 degrees, and now we're at like some angle theta. The coefficient of static friction between the block and the plane, it doesn't change. All right, remember, it's a coefficient of friction. Those things do not change. All right, and the last one, same example, except we are saying the force of static friction. Now, this is a more complicated question that I'm not totally going to do justice right now, but looking back at these pictures, the normal force was one thing right here. Here it is. Now, when we increase this angle, the normal force is going to have to change because the amount of force applied is going to have to change. So here, the normal force is just equal to Fg. But as we increase this angle, some of this Fg is still pulling it into the ramp, which means normal force has to cancel that out. But some of it is pulling it down the ramp, which means that no matter what, the normal force must be less. There's less gravity pulling it into the ramp. So because the normal force has to be less, that means the force of friction must be less. It must decrease. It must be this choice 1 right here. All right, so that's a brief going over of this work, this review book work, and so hopefully that was helpful. Please let me know if you have any questions.